everyone, welcome to Chemistry Calligraphy. I got some new nibs recently, this one, and I'm going to be using this one today. It's the one I usually use over here. And I'm also thinking about doing some pencil stuff. I got these new graphite pencils, so I might do some of these videos with soft pencils instead of calligraphy. Try that. So today I decided to do another request as usual. I have so many requests and I have a long list. So this request, though, is on a topic that is so important in our lives everywhere. And this is intermolecular forces. So I'm already out of ink. How did that happen? So, we see these everywhere in chemistry, biology, truly, you could thank intermolecular forces for life on Earth as we know it. There's some subtleties here that are just so important. So, alright, so we're going to talk about the 4 most common of intermolecular forces. And the ones I'm going to be covering are, first we'll talk about, we're going to talk about Ion-Dipole intermolecular forces. Okay, so, these Ion-Dipole will be first. Intermolecular force, it's very important, is Dipole-Dipole. Third one, there's a lot of different names for it. One is Dispersion Forces, also called London Dispersion Forces. Sometimes it's called Instantaneous Dipole. You also sometimes hear the term van der Waals forces. Those are a little bit different than these, but it's a similar idea. Let's give those 2 names. And then the last, it is an intermolecular force. It's not a bond, but it does have a name. Hydrogen. Bonding. an intermolecular force, which means, let's talk about what this means, that we have attractive forces that are between two separate molecules. It's not an attractive force between two atoms in a molecule. That would be a bond, a true chemical bond. So these are intermolecular forces. Okay. So let's go through each one of these and what they mean, what they look like, and their relative strengths. Okay. So we'll start with Ion-Dipole. Okay, so here we've got these up. Okay, so Ion-Dipole. So this is exactly what it sounds like. Now, that's assuming that you understand the concept of what an ion is and what a dipole is. So let me show you an example in case it's something you haven't seen before or you've forgotten. So I'm going to use sodium ion as an example of our ion. So sodium is positively charged after it loses an electron. It becomes an ion. And so this is how it exists in something like table salt. That's sodium and chloride ions together. Or sodium, because it has lost an electron, and electrons are negatively charged. That means that what remains is the positive charge, the sodium. So I'm going to draw a circle around to create kind of a barrier. Okay. So we can imagine this is outer sphere of where the electrons are mostly confined in here. And then we consider its interaction with a molecule that's a dipole. Okay, so what is a dipole? We're going to use water as an example of a molecule that has a dipole. So let's draw the structure of water. Okay, it's oxygen. And I did do a video that talks about geometry of molecules. And we discover that water is a bent structure, bent geometry. And if we think about something called electronegativity, that is a characteristic that all different elements have, and it gives you information about how good an element is at pulling electron density towards itself in the context of a chemical bond. So when you think about electronegativity, you are looking at a whole molecule and how does one atom compare to another in terms of how good it can pull that electron density, and if it is better than the other atom, which is the case here. Oxygen is better at pulling electron density towards it than hydrogen. It has a greater electronegativity. And that means that the net result is means that there will be more negative charge. If we were to draw an imaginary line, imagine that this is the top. You can hear Griffin walking around. That's my dog, Griffin. His little paws. Now he's trying to jump up on the couch. Oh, he made it. He has stubby little legs, so sometimes he doesn't make it up on the couch the first try, but he did it this time. Yay. Okay, so if we compare this side of the molecule to this side, because oxygen draws electron density towards it more effectively than hydrogens do, that means this side of the molecule will be more negative, slightly more negative, okay? Not a full negative charge, but just partial. And so we use designation to talk about partial charges, and that is a lowercase delta, a Greek symbol for delta. Looks like that. So we say delta, meaning partial negative. Okay, so this is a partial negative charge over here. And then, I didn't put it right there because there wasn't really room, and I want to show the interaction here. And then, this side of the molecule, it means it must be partial positive. Okay. So whenever you have partial negative on one end of the molecule, it means you must have partial positive, because there's asymmetry. Okay, so if the electron distribution is asymmetric, it means it's more on one side than the other, and you end up with a dipole. And then, when you consider the molecule that's a dipole, and how it's going to interact with the ion, this is a full +1 positive charge. So everywhere here it's the same. It's all positive. And so that's how we predict that the oxygen end of our dipole will be attracted to the positive, because in Coulombic forces, or in other words, electrostatic forces, negative attracts to positive. So we have this kind of configuration when we dissolve sodium chloride in water. Then the sodium and chloride ions break apart from each other, and the water molecules attract to each ion in this way for sodium. But then if we consider chloride ions, they are negatively charged. So once again we draw. This is just to show, here we have an ion, electrons in there, -1. Now, again, if we consider water molecule is a dipole, that's the negative side, positive side. Since chloride is negative, we now expect that the water molecule will be attracted. Oh, sorry. Sometimes. Old school ink. Okay, it's going to be attracted this way with the partial positive end of the dipole attracted to the negative chloride. Okay, so this is our, let's start one last one here. So this attraction here is an Ion-Dipole intermolecular force. Ion-Dipole intermolecular force. These tend to be relatively strong because it is a full charge. When we're looking at an ion, that means that it is a permanent ion. It's always fully -1 or +1. So this being partial negative will still be attracted, still be attracted significantly, but not as strong as if it were the sodium and the chloride when they are a solid. When it's the table salt, that's just sodium and chloride. But when you put it in water, then there's so much water about that the water molecules can very effectively separate and attract to those ions. Okay. So Ion-Dipole forces, those tend to be the strongest because it is a full charge we're talking about that the dipoles are attracted to. And that is contrast to if you just have two dipoles attracting each other. So let's talk about that. Okay, we've got dipole-dipole. Dipole-dipole. This is exactly what it sounds like. So we already drew out water, so let's continue that thought. So I'll draw water molecule here. And again, we can consider how it's asymmetrically distributed in terms of electron density. There's more electron density on this side with the more electronegative oxygen. And on this side of the molecule, less electrons means that it's a partial positive. So here's our dipole. So if we imagine the best way, the most energetically stable way for two water molecules to attract each other, we would then expect I drew that oxygen a lot smaller. These are very different looking water molecules. Okay, so hydrogen end is partial positive, negative end, partial negative. So here we've got partial positive attracted to partial negative. So in the liquid phase of water, the water molecules are moving around quite a bit. Okay, but they do attract each other in this way in terms of dipole-dipole. Now, with water, there's another intermolecular force happening that affects this as well. That's called hydrogen bonding, but we will talk about that in a little bit. Here's just one example. Let me draw another example showing dipole-dipole. And that's going to be hydrogen chloride. Okay. So with hydrogen chloride, once again, if we look at electronegativity. Chlorine is more electronegative. It is pulling electron density away from the hydrogen. So this side of the molecule, partial negative. This side, partial positive. I also wanted to mention that there's another convention for showing a dipole and where the electron density is. And that convention is more like a vector, showing the direction of the electron density, essentially. And so the way you would show it over this hydrogen chloride molecule, it's like this. This is the dipole, shown as a vector, which that crosshatch there is showing that it's the partial positive, and this arrow is showing essentially the direction that the electrons are pulled, and they're pulled towards the chlorine. So this is one way you can show the dipole. What's it called? The dipole moment of a polar molecule. Here's another way. Okay, both of them are valid. Both are useful. So the thing I like about this one is it shows the direction of the dipole, as well as just showing one side versus the other. Okay, so once again, if we looked at HCl, and by the way, when this is dissolved in water, then it becomes hydrochloric acid, but we're just looking at the hydrogen chloride molecule. So its most stable way of attracting other molecules like itself is in this way. Because once again, you get the negative, partial negative and the partial positive. I'll draw this up here just for completion. I'll draw our vector. Okay. So, I also wanted to show you that so far we've been showing how the molecules align themselves in the most energetically stable way, but we also want to take into account what would happen if we were to flip one of these molecules, such as if we had hydrogen chloride like this, then next to it the molecule is like this. Okay, now what we would observe here repulsion. Okay, these repulsive forces, that would be a partial negative next to a partial negative. So that's what happens when you configure two different molecules in this way. Okay, so keep that in mind as well. Okay, so let's move on. About the intermolecular force that has probably the most different names associated with it. Okay, so we've got, sometimes it's called the London, I'll include London in the name here. Okay, so before is, I feel like I have something at the end of my bib here. I have some paper. Okay. Alright. Another name is Instantaneous Dipole. So, there are other names as well, but these are two common names for it. Some people shorten this and just say London Forces. Some people shorten it and say just Dispersion Forces. Instantaneous Dipole, though, this is the most descriptive name, and you'll see why once I start explaining it. Okay. So I want to explain this by using an example that is one of our noble gases. Okay, so I'm going to use this xenon atom. Okay, xenon is a very large element. Okay, and it has a lot of electrons. Okay. In fact, I should look up and see how many electrons it has. Let's see. Okay, bring in our periodic table. Alright, periodic table, the elements. I'm over on the right side. There, you can see xenon. It's element number 54. Okay, the lower right. So that means that a xenon atom has 54 protons and 54 electrons around it. Okay, so that's a lot. That's definitely on the bigger side, so it's a pretty big atom. So we're going to draw a big circle around it, showing there are lots of electrons here. Okay, so remember, electrons take up most of the space. Well, I should say the atom is mostly empty space, but the available area in which electrons can reside is most of the volume of an atom. The nucleus in the center takes a very small amount. Okay, so let's consider if we have two xenon atoms that are nearby each other. So I'm going to try to draw an atom similar size. Okay, so here's another xenon. Okay, so like I said, 54 electrons here. 54 electrons here. So these electrons, they're in orbitals and they are doing their quantum mechanical dance, okay? That's beyond the scope of what we're talking about, but the take-home is that there will be a moment when perhaps decide for just an instant, you have some extra electron density. one side than the other. So there could be a couple extra electrons over here in a kind of imbalance. Alright, so there are lots of ways you can think about this. And one would be, like when people do the wave, if there's a big crowd of people and they can organize a wave, and sometimes people over here, their hands go up and then they go back down. So there is a moment when more hands are up over here than there are over here. Same thing with the electrons. Sometimes they're moving in such a way, a couple extras. So there is an instant when we have a partial negative. Okay? So timestamp 1, you can imagine, just for an instant, partial negative. So what would happen right here is that this partial negative would actually repel electrons that are on this neighboring xenon. And so if those electrons are repelled, they'd go over here. And what does that do to this side of the atom? That makes it just for an instant, partial positive. Okay? Again, this is just for an instant. Because overall, xenon is neutral. 54 protons, 54 electrons. 54 protons, 54 electrons. Charges are balanced. These are both neutral. But because of this movement, random movement of these electrons, we do get this instantaneous dipole effect from one that then affects an adjacent atom. Okay? And this goes back and forth. So for that instant, maybe it's negative on this side. And then at another different instant, the opposite could happen. You could have it switch. And it could be for similar reasons. You could have electrons move over here, making the xenon partial positive on this side, and then that would attract electrons from this xenon and come over. So for an instant, I'm going to say another different instant. This is the case. So this flow of electrons, this flow, I shouldn't say any electrons are not going between the two, but the flow of electrons and that asymmetry of electron density, of how it's distributed within one atom, will affect the distribution of electrons in a neighboring atom. And that is the origin of the instantaneous dipole, or London dispersion forces. So this is very commonly seen with atoms or molecules that are non-polar, but it also happens with polar molecules as well. It's just that with dipole-dipole or ion-dipole, the dominant forces are the dipole interactions. The London forces don't dominate. But when you have non-polar atoms or molecules, this is the dominant intermolecular force that happens. What's interesting is that it sounds like these would be quite weak, which is true for some cases, such as the noble gases, like the case of xenon and helium, it's even weaker because there are fewer electrons. But if you get really large molecules, then you have so many cases for different parts of the molecule for this to be happening. And the intermolecular forces can be quite strong, surprisingly strong. So if you look at something like asphalt, asphalt on the roads, those are long chain hydrocarbons, and the interaction, the intermolecular forces between the different long chain hydrocarbons, many are these instantaneous dipole interactions. And because those molecules are so large and so long, that there's a lot of chances for attraction due to instantaneous dipole along the length of those hydrocarbons. So they can be quite strong. It's also the one pretty well-known example is gecko feet. Our little gecko creatures. Geckos can climb up walls and they can hang out on the ceiling because they're very strong intermolecular forces that are instantaneous dipole between their feet and the walls and the ceilings. So they can be pretty strong, as I said. Okay. Let's talk about a little bit more room here. Okay. Let's talk about hydrogen bonding. Okay, hydrogen bonding. Oh my goodness, there's so much to say. Alright. So with hydrogen bonding, I said it before, and just wanted to remind you that this is not a true chemical bond. This is, even though it has the word bond, this is an intermolecular force. Okay. Hydrogen bonding, this occurs between guess what? Hydrogen, as you would. But specifically, hydrogen that is bonded to fluorine, oxygen, move this over a bit, or nitrogen. Okay, so it's between hydrogen, and then here's our qualifier. It has to be bonded to one of these. And one of those, okay? And specifically the lone pairs. On that fluorine or the oxygen or the nitrogen, depending on what molecule you're looking at. Okay, so we already talked about water, so we can look at that again. So we already saw with water we have dipole-dipole interactions, but now we have another type of interaction that can happen. So I'm going to draw the water. I'll draw it again this way. Bend structure. Okay. So I talked about the electronegativity of oxygen being quite high. Okay, is second only to fluorine. Fluorine being most electronegative element on the periodic table. But oxygen is in second place, so it is drawing electron density away from hydrogen so effectively that the hydrogen atom only has a small amount of electron density around it. A lot of it is stretched over the course of the bond between them. Okay, so that leaves quite a strong partial positive charge here. Meanwhile, we've got these lone pairs. And lone pairs, of course, there's 2 electrons in this orbital here. 2 electrons in this orbital. So, these are quite strong in terms of the partial negative charge. Right? So what that then allows is, and I'm going to draw with a dashed line, is that there could be a strong interaction between the oxygen, lone pair on that oxygen, and hydrogen on a neighboring molecule of water. Okay, so here specifically this interaction is our hydrogen bond. So as you can see, it's not a true bond that's part of the molecule. Here's the molecule. There's a covalent bond here. This is a sharing of electrons. It's quite a strong bond. Here and here. These are considered to be chemical bonds. Permanently there when it's the H2O molecule. This hydrogen bond, however, is an interaction. It is an intermolecular force. Okay. But again, it does have to do with this strong negative, partial negative charge here, and partial here. But it is different than dipole-dipole because it is a specific interaction between one of these hydrogens and the lone pair of the oxygen. It's not that general partial positive, partial negative attraction that we saw with dipole-dipole. Because this hydrogen here, it can have its own hydrogen bond with another water molecule. Okay, so each one can have that and its own interaction. These are quite strong. Okay, they can be close to that attraction of an ion-dipole interaction. Alright. And the result of this is it makes water. It's one of the reasons why when water freezes, the hydrogen bonds make a structure that's a really interesting 3-dimensional hexagonal type structure that is less dense than water when it's a liquid, when these molecules can nestle up against each other a lot more closely as opposed to being separated out from the hydrogen bonds. So that is the reason why ice floats on water. That is the reason why when lakes freeze in the winter, sheet of ice on top. And that allows the fish and other aquatic creatures to live over the winter, even though it's very cold on the top. They can still survive down underneath. If this wasn't the case, if we didn't have hydrogen bonding, and if water froze in a more dense structure than it is as a liquid, everything would be different. Everything on Earth would be different. The fish would not survive in the cold climates in the winter. If the lakes froze from the bottom up, it would be totally different. And by the way, this is unusual. The solid form of water being less dense than the liquid form. It's very unusual. Most molecules do the opposite. The solid is more dense. So water is extremely rare in that sense. And because we have so much water on this planet, it's astounding the difference it makes. I could also talk more about the role of hydrogen bonds in DNA, but I did talk about that in my video about nucleic acids. I talked about nucleic acids and DNA and RNA, so you could learn about another application of hydrogen bond in that video if you want to watch it. Alright, well, there is our overview of intermolecular forces, so thank you for joining me and for hanging out for this beautiful conclusion of hydrogen bonding and water, and I just love all of that. So I do love chemistry for what it is, but I also love it for the explanations it gives us and the appreciation that it gives us for nature and the world around us. So please, as always, I say this every time, but I'm just gonna keep saying it, that any requests you have, do not hesitate to let me know. So somewhere in the comments, just let me know what you would like to learn more about, or have me explain or draw. And I'm going to be trying the pencil sometime, so watch for that. In the meantime, have a wonderful day. I'll see you next time.